Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. In my last lecture, I talked about Chapter 21 in A Student's Guide to the Great Physics texts, where we're looking at the work of Thomas Young, his lectures on light and colors. We're focusing on his explanation of thin film interference. You might remember what this phenomenon is if you have a thin layer of transparent material, such as an oxide layer on top of steel, and you illuminate this with some light, then the light is going to bounce off of the top surface of that oxide layer and also the bottom surface of the oxide layer. And in the event that those two are constructively interfering with one another, that is, the two reflected beams are constructively interfering, then that layer will appear bright, and in the event that they are destructively interfering, it will appear dark. So let's do a quick example problem, and then what we'll do is we'll go on to talk about soap films. So suppose we have a thin layer right here. Let's suppose this is a surface that has perhaps a refractive index of 1.5. I'm just going to make up some numbers here. Suppose this has a refractive index of 1.25, and suppose this has a refractive index of 1. So maybe this is air, I'll call this medium 1. Maybe this is some kind of film of oil, that's layer 2, and this is some other substance like glass. And let's suppose that we have light that is illuminating this from the top, and the light is bouncing off the top surface, and there's light bouncing off the bottom surface. And in the event that these two are constructively interfering, you will see a bright color when viewed from above. And let's suppose that the wavelength of light that's incident in this from the air is, maybe about 500 nanometers. So this corresponds to kind of a cyan color, kind of a bluish green light, like a robin's egg. Okay, so what is the thickness that this film would have to be so that there would be constructive interference and it would appear bright when viewed from above? Well, if the thickness of the film is T, let's just call that thickness T, we need a situation where 2T is equal to 1 lambda or 2 lambda or 3 lambda or some other number, integral number of wavelengths. So the thinnest film we could have would be if it's exactly equal to lambda. But keep in mind that this needs to be the wavelength in medium 2, because we need to fit exactly one wavelength in this medium. Okay? So what we're going to have to do is have to have the thickness of the film be the wavelength in that medium divided by 2, kind of solving this equation. So the next question we have to ask is, what is the wavelength in medium 2? Well, we know the wavelength in air is 500 nanometers, so the wavelength in medium 2 is going to be the wavelength in the air divided by the refractive index of medium 2. So that would be 500 nanometers divided by 1.25, or 5/4 would be the refractive index of medium 2, and so you would get 500 divided by 5/4 would be 400 nanometers. In other words, the wavelength in this medium is slightly shorter than the wavelength in air. It's 400 nanometers. Okay? And so solving our problem, we can see that the thickness of the film must be 400 nanometers divided by 2, or 200 nanometers thick. So if this is 200 nanometers thick, then you'll have constructive interference. Okay? So that's a quick example problem to work out for thin film interference. You might also imagine if you made this just the right thickness, let's say this was a half of a wavelength, if 2T was a half of a wavelength, that is, T is 1/4 of a wavelength, so maybe I'll just say this. If T was equal to 100 nanometers, then by the time this wave travels through on the way down and back up, it will have gone through 200 nanometers, which is half of a wavelength, and it will be destructively interfering, and that would mean that the film would appear dark. So you could, if you made this coating, let's suppose if this was glass down here, and this was some kind of coating, and this was air, then if you make it just this thickness, then all of the cyan light that's impinging upon it is going to be non-reflected, and so you'll have an anti-reflective coating for this wavelength. So this is something that optical engineers are interested in making anti-reflective coatings for glass lenses, for example. Okay, Now, the next thing that Thomas Young talks about that I like to focus on is a very fascinating topic, and that is also related to thin film interference, but in the case of soap films. So he mentions, if you look at page 250, about the middle, he says, thus, when a film of soapy water is stretched over a wine glass and placed in a vertical position, its upper edge becomes extremely thin and appears nearly black, while the parts below are divided by horizontal lines into a series of colored bands. Okay, so what is he talking about there? Let's talk about this thin film interference. He's saying if you take a wine glass and you lie it on its side, you lay it on its side like this. So I'm going to have a wine glass that looks like this. After you've dipped the end of it into a soapy film, then the soap film is going to be stretching over the rim of the wine glass. And what he says is you'll see a region on the top that's very dark or black, so kind of a black film in the top. I'm going to kind of shade this black to indicate that this is a soap film, but it appears completely dark. And then below that, you're going to see this sort of this colored fringes down here. So I'm going to draw like these fringes like this. Why would this happen? Well, once again, this is a case of thin film interference. So let's look at this from the side and see what's going on. I'm going to kind of zoom up on this side right here. This is supposed to be the wine glass. And then you have this soap film stretching like this. And it is thicker as it goes down, like this. So this is your soap film, and it's thick at the bottom because of gravity. The soap is flowing downward, and it's very thin at the top. Now, if you were to illuminate this with, let's suppose, red light, and look at it from this same angle, that is, look at it from over here, so this would be your eye looking at it, well, the red light is going to bounce off the top surface and also bounce off the bottom surface and come back to you. And just like in this case I explained above, and just like the case of thin oxide films, those can either constructively or destructively interfere with one another. And you can probably see that because the thickness of this film varies with position, that is, varies as you go downward, the thickness is going to vary, and hence you're going to have bands of constructive interference and destructive interference and constructive interference and destructive interference, as for example, one wavelength of light or 1.5 or 2 wavelengths or 2.5 or 3 wavelengths and so on can fit inside of that film. And that's precisely what you see. So notice that I'm going to show an image here of a soap film stretched over a wire, a copper ring that I took in my laboratory, and this is a short movie you can see, and you can see these horizontal fringes of red and red light and blackness, and this has been illuminated with a sodium lamp, which produces kind of a reddish orange light. So you can see exactly what Young is talking about here. Now, there's an interesting issue that he mentions that I'd like to come back to, and that is that at the top of the film, it appears black or very, very dark. So why would it appear black or very dark at the top? After all, if the light is reflecting off the top and bottom surface, if it's reflecting off the top surface and the bottom surface of this, and it's very, very thin, you'd anticipate that as the thickness, as t goes to 0, as t approaches 0, then the beams, then the light reflecting off the I guess bottom surface, in this drawing it'd be on the left surface, the bottom surface of the soap film would be in phase with the light reflecting off the top surface, or in this case the right surface, right? So as this thickness gets closer and closer to 0, then these two beams, beam 1 and beam 2, 1 and 2, reflecting off the back and the front surfaces, those should actually approach being exactly in phase with one another, so one would anticipate you would have constructive interference between those two. So why would it appear black? Well, there's a point that we've left out up until this point, and that is the issue of what is called the reflection phase shift. Reflection phase shift. And we wouldn't know about this if it wasn't for experiments like what we're showing here within soap films, and it's this. When you have light reflecting off of a surface that has a higher index of refraction than the medium from which it's coming, then there is no reflection phase shift. It's just exactly like we've been talking about up until now. But if the light is reflecting off of a surface that has a lower refractive index than the one from which it is coming, then there's immediately a 1/2 of a wavelength phase shift. So looking back up to this diagram at the top, notice that when the light was coming from air and reflecting off of the coating had a higher refractive index, 1.25, than the air, and hence that does not suffer a 1/2 wavelength phase shift. We could simply ignore that. And likewise at the bottom surface, the light was reflecting off the glass, which had a higher refractive index than the coating. So once again, there was no reflection phase shift, or no 1/2 a wavelength phase shift. But if, on the other hand, and I'm going to use this corner of my diagram up here, if we have a situation where we have air and then soapy water, and then air once again, here we have a refractive index of 1. Here we might have a refractive index of 1.2, let's say, and here we would have a refractive index of 1 once again. So if we have light reflecting off the top surface, notice here there is no reflection phase shift, so we treat it just like we have been. But when it reflects off the bottom surface, it's reflecting off of a medium that has a lower refractive index than soap, so immediately at this interface, there's a 1/2 of a wavelength phase shift. So in addition to the extra wavelength that it goes through in traveling this extra distance t, so it goes an extra distance 2t and acquires some phase from that, there's also an additional 1/2 of a wavelength phase shift that it acquires simply upon reflection. And that's exactly why the top right here is black, because although there's no extra distance traveled by beam 2 compared to beam 1 when the layer is very, very thin, there's immediately a 1/2 a wavelength phase shift of beam 2 as it reflects off the bottom or the left surface of the soap film, and that puts it exactly 180 degrees or a 1/2 a wavelength out of phase with beam 1, and thus there's destructive interference. So that is what Young is talking about in this section. And I have here, like I said, I have some soap film images that you can see this sort of thing, and I think what I'll do is I will end this video with a few other images of soap films that I took in my laboratory to kind of illustrate the beauty of soap films and the fun of studying them.